So in this video, I'm going to go over exponential functions. So the essential question today is how can equations describe growth and decay situations? And the learning objective is to write and evaluate exponential expressions to model growth and decay situations. So first of all, we have a couple vocab words here. So an exponential function has the parent function of f of x is equal to a times bx, where a represents growth or decay. Actually, where b represents growth or decay. We can, which we'll study later, and the base b is a constant, and the exponent x is the variable. So when we're talking about these problems, and we have an a out here, what that means is that this right here, that term right there is going to determine whether it's growth or decay. So if it's growth, then that b is going to be greater than 1. And if it's decay, b is going to be a decimal. So it's going to be between 0 and 1, like this. So that means it's going to be a decimal or a fraction. Move this out of the way. So this first graph says the graph of the function f of x is equal to 2 to the x power is shown. The domain is all real numbers, and the range is y values such that y is greater than 0. So now why is that true? So everybody look here. This line right here is what we call an asymptote. And if you notice, the graph is approaching that line, but it's never actually going to touch that. This is how I know that. As we move to the left here with our x values, notice that this is 0, -1, -2. What's happening to these values here? Aren't they getting smaller? Do y'all notice that? Okay. So our y values are getting smaller, but they're never going to reach 0. Okay. So this has an asymptote of y is equal to 0. The graph is going to approach that, but it's never actually going to reach it. Then it says up here, notice the x values decrease. The graph of the function gets closer and closer to the x-axis. The function never reaches the x-axis because the value of 2 to the x power cannot be 0. In this case, the x-axis is an asymptote. And so that's spelled A-S-Y-M-P-T-O-T-E. An asymptote is a line that the graph function approaches as the values of x either get very large or very small. And what is the end behavior for this graph? Okay, so what does that mean? So that means over here, as I approach infinity over here with my x values, what's happening to this graph, y'all? Where's it headed? Is it headed towards infinity up there? And as we head this way towards negative infinity, what's happening to the graph? Notice it's going to approach y is equal to 0, but it's never actually going to reach it. So f of x there is going to be 0. So now when we talk about this next one, we're going to talk about the asymptote, the intercepts, all of this. So the first thing I want to ask you, though, is based on what this value is right here, is this growth or decay? Hopefully you can see, because it's a fraction, it's going to be a decay function, okay? So then, once again, we're talking about our asymptote. Now with all of these, the asymptote is going to be right here, which is what? That's going to be the x-axis, so y is equal to 0. And let's go ahead and graph this, and we're going to then talk about the intercept. So I went to Desmos, and I'm going to actually put this equation into Desmos. So I'm going to do 10, maybe, if I can get my mouse up there. 10, and in parentheses, I'm going to put the 3/4, and then I'm going to take that to the x. I'm going to go Shift 6 to take, go out of that parenthesis, and then I'm going to do Shift 6 and take that to the x power. So hopefully you can see this graph, and I'm going to move it over so we can see a little bit better, and I'm going to zoom out. Can you see that the y-intercept of this graph is at 10 right here, 0, 10? Y'all see that? And we could actually plot a couple other numbers here. So when we're at 5, it's at about 2.5, and when we're at 10, it's about at 1/2. Okay, so when we go back to our graph over here and we talk about what those points are, first of all, we know that it's crossing the x-axis up there. That's our y-intercept. So this is going to be 0, 10. Okay. Then we said also that another point. So if I look at 3, I was at 4.2. So that's about there. And again, I can pull any numbers I want. And I said at 10, it was about 1/2. Remember? So this is our graph. And again, I'm not looking for perfection here, just looking for a good representation. Okay. So now let's talk about our end behaviors. So as I move towards infinity here with our x values, what's happening to the y? Check out right here what's happening to it. Isn't it approaching 0? It is going to approach 0, but it's never going to reach it. Now as I move towards negative infinity over here, what's happening up here? Hopefully you can see that it's headed towards infinity up here. So those are our end behaviors. Now when we talk about domain, notice our x's are going to keep going to the left and to the right. So our domain is going to be all real numbers. And then our range, notice what's happening with our range. Our range is only above the x-axis, or y is equal to 0. So our range is going to be y is greater than 0. Now this bottom question down here says, do you notice a correlation between the y-intercept and the equation? And hopefully the answer to that question is yes. So let me erase this up here so we can look at the equation. So do y'all see this 10 right here? Notice that 10 right there. So that's what determines what our y-intercept is, okay? All right, so this next one, first of all, question, is it growth or decay? Because it says before you graph, is there information from the equation that can help you make a hypothesis about what the graph looks like? So that right there tells us it's growth, doesn't it? Okay, so then it says we're going to graph the function again. So I'm going to again go back to Desmo, so hold on. So I went ahead and put that equation here, but I don't even see it, so I need to zoom out. Check that out, okay? So notice it's crossing at 100. Let's look at a couple other points here. So let me zoom in a little bit. So if we're at, because our graph only goes to 10 or negative 10 over here, y'all. So I'm going to zoom down here and I'm going to see where does it intersect at negative 10. Looks like it's 60. And then I'm also going to go over here to the right. And again, notice how this 10 is moving with us, right? Okay, so because we want to see where does it cross at 10. So at 10, it's like 162-ish, somewhere like that. A little bit. If I go up a little higher, there. So it's like 162, yeah. So when we go to graph again, let's go back here. And we will plot those points again. So first of all, you should notice that it crossed at 100, right? And we knew that already. Why? Because we talked on the last problem that that's going to be my intercept, right? Okay. Here again, my asymptote is this right here. It's going to be that line, and it's always going to be that for these problems. So it's going to be y is equal to 0. Now we're going to go ahead and plot those points that we got. So I got, trying to go back to my numbers here. So when I was at negative 10, I got 2. So that's like way down here, right? And then when I was at 10, I got 163. So we'll say it's about like that, right? So this almost looks like a straight line. It's really not going to be, but it kind of looks that way from here. Okay, so that's our graph. So here we go again. End behavior. So as we move this direction now with the x values, our graph is moving towards infinity, isn't it? It's going up. And as we move towards negative infinity over here, it's going to again approach 0. Because remember, it's never going to go below that asymptote. And again, our domain, nothing is limited. We've got arrows on either end. So our domain is going to be all real numbers. But our range, again, is going to be y is greater than 0. All right, so this one, you guys need to pause the video here. Go ahead and try this and then come back to me when you're done. So this one is again a growth because that's greater than 1. Okay. Our asymptote is still going to be y is equal to 0. So it's going to be right here like it's been all along, right? Hopefully by now you've noticed that all three of these, the asymptote was there. Okay. Now we're going to pull this point, 0, 5. That's going to be our intercept. That's going to be right there. Okay. Now, because this is growth, again, I'm going to find some points. So I'm going to go over here to the left, and I would put this in decimals again. And at the left, it was negative 10.8 there. And then all the way, if I go over here at 4, it was 10. Okay. So my graph is going to look something like this. Okay. Again, growth. So it is rising from left to right. Makes sense, right? So here we go again. As we go towards infinity here, where's our graph going? Towards infinity up there. And as we head towards negative infinity over here, where's our graph headed? Towards 0. Remember I said domain is all real numbers, and the range is going to be y is greater than 0. So if you guys miss asymptote, domain, and range for these questions, that means you did not take the notes. All right, so this next part says you can model growth or decay by a constant percent increase or decrease with the following formula. So these, we're going to talk about this. This is the initial amount that we are using for the problem. So it's going to always give us an amount that we're starting with. Then we're going to talk about the rate. That's what this is right here. That's the percentage. And then this is going to be our time. Okay. So it says in the formula, the base of the exponential expression 1 plus r is called growth rate. Okay. That's what this is called. And what does that really mean? That means it's a rate of increase. Okay. And then when it's 1 minus, that's going to be a decay rate, which means it's a rate of decrease. And hopefully this will help you decipher these problems as we're talking through them here in a minute. Okay. So this is our first example. So it says Claire invests $5,000 in an account that pays 6.25% interest per year. How much will she have in the account after 5 years? Just from the information given, can you hypothesize about if this is increase or decrease, growth or decay? So hopefully you know that the money's going to grow, right? So this is going to be growth. Okay. Write the function to model the growth in the value of her investment. So I want to talk through all of this, and I'm going to actually work this problem down here on the bottom, just talk you guys through it all, okay? So first of all, it says $5,000. So I want to go ahead and write my formula, a to the t and equals a 1 plus r to the t. Okay, so this a right here is our initial investment. It's $5,000 right there. Okay. Then I got 1 plus r. That is our rate of interest right there. Now here's the part about this I want to show you guys. If I have 6.25 and I want to change that to a decimal, then I have to move my decimal 2 places to the left. So what we're going to put in here is 0.0625. And then our time was the 5 years. Okay. So then we're just going to put those in, and I'll show you guys how to do this in decimals. So you guys are going to really love this. So we're going to put the 5,000, and then we're going to do 1 plus 0.0625. And we're going to take that to the 5th power, right? Notice it gives you the answer right there, $6,770.41, okay? Now we're going to go back here, and we're going to work a couple more problems. So that was the answer to this problem. And all that work is right here, but I wanted to go ahead and show it to you guys in Desmos as well, so, and how to set it up. So let's go on to the next problem. So this one says in 1981, the Australian humpback whale population was 350 and increased at a rate of 14% each year since then. What is the first decision you have to make after reading the problem? That's whether it's growth or decay, and it is growth. How do we know that? Because it said increased right there. Okay, so now we're going to write the problem, 350. 1 plus, remember this is going to be 0.14 because we're going to move this 2 places to the left. And then our time down here is going to be 5 years. So again, we can put that in decimals just like that, and it's going to give us 673.9. And the answer really would be 673 because we can't have a 0.9%. We can have a 0.% of a whale, okay? All right, so this one says the city population, which was initially, so here we go, our initial amount's right there. And we're going to go 1 plus plus dropping. Y'all notice that dropping right there? So this should be minus, okay? See you guys. So we're going to do 0.03, and again, we're going to put our 10 years up here. So when we put this in the calculator, we get 11,430. All right, so the next one has to do with compound interest. Now this is important because when you guys go to buy your first car, they're going to give you different ways of purchasing it if it's a brand new car. And so this how things are compounded is really important. So it says A is the amount earned over time or that you paid for something. P is the principal or initial amount. R is the annual interest rate. T is the time in years. And N is the number of compounded periods. So annually would be 1, semi-annually 2, quarterly 4, monthly 12, weekly 52, and daily 365. Keep this table because it's going to be important as we move through the next set of problems, okay? So on this one, we're going to do each of these. So it says you invest $500 in an account that pays 7%. Calculate the total amount you have after 8 years. So our initial amount's 500. We're going to do 1 plus. Now we're going to do 0.07 divided by 1 because n equals 1 here. That's annually, right? So then we're going to do 8 times 1. And again, we can do this right in Desmos. And when we do, we get $859.09. Now, when we do compounded monthly, n is going to be equal to 12. So we're going to do 500 times 1 plus 0.07 divided by 12. And then we're going to do 8 times 12 out here. Okay? When we do that, we're going to get $873.91. And lastly, when we do compounded daily, we're going to do n equals 365. So this is going to be 500 times 1 plus 0.07 divided by 365. And we're going to multiply that 8 times 365 out here. Okay? When we do this one, we get $875.29. So then it says, what can you conclude if the numbers are similar? Well, obviously, there's not a big difference between monthly and daily, is there? So, obviously, they would, and what you really should notice here is that the more frequently something's compounded, so like when it's compounded daily, we earn more money, but we also, if we're borrowing money, we spend more money, okay? So, if you're trying to earn interest, then compounded daily is great. If you're paying for interest, then compounded annually is great.